Hello, welcome to the lecture on 2.2. Today we're going to talk about graphs of functions. The graph of a function. If f is a function with domain D, then the graph of f is the set of ordered pairs f of x such that x is an element of the domain, plotted in the coordinate plane. What this is saying is that we have coordinates x, y. It's just that y is replaced with f of x. So in a sense, this really just means that y is equal to the f of x. It's equal to the output. It's equal to the output value given x as an input value. So for instance, if we had a function that looked like this. So if x was 1 and f of x was 3, and x was 2, f of x was 5, x was 3, f of x was 7, and so on, then f of x becomes the y-coordinate in the ordered pairs on the plane. So here, this would correspond to the coordinate 1, 3. This would correspond to the coordinate 2, 5. And this would correspond to the coordinate 3, 7. So if we were to plot these values, it would be 1, 3, 2, 5, and 3, 7. So our function would look like this. And yes, this is a function, even though it only has 3 points. Remember that the definition of a function is that there's exactly one output for any input. Our input values are 1, 2, and 3, and each maps to a single output. So this does qualify as a function. Recall, any point x, y that satisfies an equation is contained in the graph of that equation. Remember that a lot of times our functions look like this. F of x is equal to, say, x squared plus 4. Now this is corresponding to the same thing as saying y equals x squared plus 4. If we have an ordered pair xy that satisfies this equation, then it's contained in the graph of this function. We're going to list off a few definitions of different types of graphs. A constant function has the form f of x equals c, where c is a real number, or y equals c. A linear function has the form f of x equals mx plus b, or y equals mx plus b. A power function has the form f of x is equal to x to the n, where n is an integer, or y equals x to the n. A root function has the form f of x is equal to x to the 1 over n power, where n is an integer, or y equals x to the 1 over n. Remember, f of x and y are essentially the same thing. Y is referring to the coordinate plane. F of x is referring to the algebraic rule of the function. Let's do an example here. Graph the functions a, f of x is equal to 1/2 x plus 1. B, f of x is equal to 3. And C, f of x is equal to the square root of x. Now to do these three, we're going to plot points. Later on, we'll get into a few of what we call parent graphs, but for right now, we're still plotting points. So for part A, if we're graphing f of x is equal to 1/2 x plus 1, then this is the same thing as saying y equals 1/2 x plus 1. So we need to plot a few points. I'm going to plot x is equal to 0, which would mean we would have 1/2 times 0, which is 0 plus 1, so that would just give us 1. And x equals 2. And then we would have 1/2 times 2 is 1, and 1 plus 1 is 2. Now the reason I use 2 instead of 1 is because the denominator is 2. So I'm choosing an even number so that it cancels nicely with the denominator here. Now if I plot these 2 points, 0, 1, and 2, 2, then I get this graph. And that will be the graph of part A. Again, lines only require 2 points to graph. For For part B, we actually we don't even need a point. Constant functions are always horizontal lines like this. It's the same thing as saying y is equal to 3. So we go up to where y is equal to 3 and we plot a horizontal line. Now, a vertical line is obviously not a function, and you might try to verify that on your own. But horizontal lines can be graphed y equals some number. For part C, I'm going to plot some very specific x values. I'll try to explain why I'm doing it in this way. So let's start with x equals 0. And I'm choosing 0 because 0 has a nice square root. So the square root of 0 is 0. So we end up with 0, and f of x will also be 0. Now I'm going to choose x equals 1. And why am I choosing 1? Also because it has a nice square root. Square root of 1 is 1, so we get this. Now instead of choosing 2 or 3, I'm going to skip straight to 4 because 4 has a nice square root. Whenever you're plotting functions, you want to keep the function in mind and try to choose x values that will go nicely into that function. So here, the square root of 4 is 2. So I get these 3 points, 0, 0, 1, 1, and 4, 2. So we get something that looks like this. And I want you to try one now. Graph the function by plotting points. F of x is equal to x cubed. For this function, you're going to want to plot positive and negative values to see how it looks. All right, the next topic I want to talk about is graphing piecewise defined functions. Like we talked about before, a piecewise defined function has different parts to its graph. Those parts of the graph are dependent on the conditions that x needs to meet. Recall, piecewise defined function uses different functions when x is in different parts of the domain. As an example, we want to graph the following function. F of x is equal to square root 1 minus x and negative x minus 1 quantity squared. X is less than 1 here, and when x is greater than or equal to 1 here. All right, so whenever x is less than 1, we use this function. And whenever x is greater than 1, we use this function. So let's look at these very quickly and try to get domains. Really, I only need to talk about the domain of the first part of the function because it's the only one that will be excluding x values. In this one, we have a polynomial, so the domain is all real numbers. And we'll talk about that in a bit. Here, 1 minus x needs to be greater than or equal to 0 in order for this function to be defined. Otherwise, you would be taking the square root of a negative number. Now, if I add my x over, I end up with x being less than or equal to 1. So if x is less than or equal to 1, this function is defined. So it's fine, because we're on the region where x is strictly less than 1. So any x value that's in this region is already within the domain of this function. So let's get to graphing really quickly here. So if x is equal to 1, we would get the square root of 0. Now this isn't actually a part of this function because when x is equal to 1, we use this function. I need to know how far to go with the graph since we're going up to but not including 1. I'll explain a little bit more as I graph this part. If x is equal to 0, we get square root of 1 minus 0, so the square root of 1, which is 1. And then if x is equal to negative 3, then we have 1 minus a negative 3, so 1 plus 3, which is 4, and the square root of 4 is 2. Before I graph this function, I'm going to look at how this other one is going to be graphed. So for this one, if x is equal to 1, then what does negative x minus 1 quantity squared look like? Well, if x is equal to 1, we get 0 squared. Negative 0 is 0. If x is equal to 2, then we would have 2 minus 1, and 2 minus 1 squared is 1, and negative 1 is obviously negative 1 here. And then I'll do 3, and this will be the last point that I do. If I plug in 3, I get 3 minus 1 is 2, 2 squared is 4, so we get a negative 4 because of the negative out front here. So now what I want to do is I want to show you how to graph this. But first, let me draw a green line here. This green line is not actually a part of the graph. It's just meant to separate the different functions we use to graph f of x. So notice that I graphed it at x equals 1. It's because our functions are separated by 1. 1 is the boundary between these two functions. Right? So if we're to the left of this green line, we're going to be graphing this function. If we're to the right of this green line, then we're going to be graphing this function. Now, on the left side over here is this top function, so that's what I'm going to graph first. Now remember, 1, 0 is a part of this graph, but it's actually not touching this point. 1 is not a part of the region in order to use the first function. So since 1 is not here, we draw an open circle. We do need this open circle though, because when we plot our second point, we're going to have a lot of points that come down to here, like this. So I need to know where I'm going. I need to know where to connect these two lines. So this is still necessary, but you graph it as an open circle because, again, it's not a part of the region in which we use the function square root of 1 minus x. So let me plot the other point, negative 3, 2. 1, 2, 3, 2. And then we will connect here and continue like this. So this function looks like this on the left. Now on the right of 1, we graph this function, and that will be these points here. So I have the point 1, 0. Now, since 1, 0 is actually a part of the region that we use to graph this function, I do plot a closed dot for this coordinate, 1, 0. 1, 0 is the same one as here, so all I'm going to do is fill in this circle now. It would be open if this side was the only function that had this point, but because both sides have it, we close the dot. Okay. Now I plot 2, negative 1. And I plot 3, negative 4. 1, 2, 3. This. And it's going to look like this. This is supposed to be a little bit sharper, but it's okay. So this is roughly what this graph is going to look like, the graph of this function. Now remember, this green line is not a part of the graph. It's meant to separate between these two functions, so I know which side to graph where. All right, I want you to try one now. Graph the function f of x is equal to negative 1 on the region x is less than negative 1, x on the region between negative 1 and 1, including negative 1 and 1 on the region x greater than 1. And the next topic I want to talk about is the vertical line test. A curve in the coordinate plane is the graph of a function if and only if no vertical line intersects the graph more than one time. Now, to think about this and to show you this concept, we need to recall what a function is. A function f is a rule that assigns to each element x and d exactly one element. So what we mean by this is that the output is exactly one element. So if I have a curve that looks something like this, then what does it mean for an output to have exactly one element? Well, that means that at a given x value, this point here is the output of the function. Remember, x is the independent variable, the y would be the dependent variable. So this point here, this y value, the height, the y value here, would be like the output. Well, if a vertical line intersects a graph more than one time, what we're saying is that for this particular x value, we have multiple outputs. So we're assigning to an x multiple values in the range. That's not possible for a curve to be a function. So this particular graph would not be a function. Something that looks more like this would be a function. Notice that every vertical line intersects the graph at most one time. Now, it's also fine if the vertical line doesn't touch the graph at all. That's okay. That's not a problem. But it can touch the graph at most one time. That's the important part for a curve to be a function. Try one. Determine if the following is the graph of a function. All you needed to do is determine if this curve is a function or not. The last thing that I want to talk about is what different types of graphs look like, so that we have an idea when we go in and graph them. Start with linear. So if you have something that looks like this, it's just a horizontal line, then you actually have the graph of a constant. A constant is a linear function, but it has the form f of x is equal to b, where this would be your b. Now, most linear functions have the form f of x is equal to mx plus b. And they look more like this. Either a positive slope or a negative slope, but they're the graph of a line. Then we have power functions. Now, power functions have the form of x to the a, where a is an integer. A parabola that looks like this is of the form f of x is equal to x squared. Now, we could also have a cubic function, which will look more like this. Now, I want to note here that when it starts to flatten out at the bottom, it's between -1 and 1. So, because if you take a number between -1 and 1 to a higher power, it will actually get closer to 0. So think of it in terms of like 1/2, for instance. If you square 1/2, you get 1/4, and 1/4 is actually smaller than 1/2. So if you square a number between -1 and 1, you actually get a number that's closer to 0. I'm only going to do the fourth function here. F of x is equal to x to the fourth. This is just a flatter version of f of x is equal to x squared. So it's a steeper and it's flatter between -1 and 1. And that should make sense because numbers between -1 and 1, when they're taken to a fourth power, will be even closer to 0 than if we only squared them. Similarly, if we showed f of x is equal to x to the fifth power, it would be a flattened version of f of x equals x cubed. Root functions. Now, there's really two that you need to know, namely the square root, that looks like this, and the cube root. Now, remember, when you have an odd index on your root, the domain is all real numbers. So you're going to have something that looks like this. Even negative values produce an output. This one would be f of x is equal to the square root of x, and this one is f of x is equal to the cube root of x. Now, every odd indexed root will look something like this. It'll be a little bit flatter horizontally. It will go off towards x equals infinity faster. It won't rise as much here if we have a higher index, a higher odd index. If we have a higher even index, the same thing will happen. it'll go up to x will move towards infinity faster. The y value will grow slower. And then we have the reciprocal functions. Specifically 2. F of x is equal to 1 over x, where you have an odd power on the x. And this looks something like this on the positive side, and then like this on the negative side. And then if you have an even power, because when you square a negative number, you get a positive number, you would end up with something like this. It'd be a little bit steeper towards the 0. So as we get closer and closer to 0, this would be steeper when you have f of x is equal to 1 over x squared. Now that's true for any power. If the power on x increases, then this will be steeper and steeper. But if you have an even power, then you'll have this phenomena where you have the curve is above the x-axis. And then if you have an odd power, you'll have half of the curve above the x-axis and half the curve below the x-axis. Again, if the power is a higher odd power, it will be steeper here and it'll be shallower here. The reason that we're going over these is so that we have these parent graphs. So later on, when we talk about graph shifting, we'll use these graphs to move them around in the plane. And then we'll be able to stretch them and compress them and shift them throughout the plane. You definitely need to know the linear and the power functions. Probably up to x to the 4th power is probably good. X to the 5th is stretching it a bit. Root functions, you definitely need to know both of these, the square root and the cube root. And the reciprocal functions you need to know as well. All right, that's going to be it for today. I will see you all in the next lecture.